My name is Jeff Franklin. I am the original architect of the commercial software package called Azore. My contact information, I can be contacted through LinkedIn or through my email address here. I'd like to talk today a little bit about turbulence model predictions and kind of trying to assess the difference between a quantitative prediction and a qualitative prediction. And to do that, we're going to use a U-Bend benchmark to kind of help us with that perspective there. So let's get started. So the first thing I'd like to talk about is really what is the purpose of a turbulence model. And the first thing you want to understand here is that a turbulence model, it really wants to try to capture these transient eddy flow structures that are always around. So like a small structure is a small eddy that maybe grows and shrinks, but it's at a very small length scale and it grows and shrinks very rapidly. They're also very large flow structures, like if you're outside in an ambient condition, you might feel like a gust of wind hitting you, maybe 1 minute and then maybe another couple of minutes. So those eddies are very large structures and they occur over a long period of time. And our turbulence model, its job is to try to kind of capture those effects. There are also subgrid scale secondary flow structures. So at some point, we can't really capture the flow structures with our mesh because our mesh length scale is too large for those flow structures. And some of them we can capture because we have enough definition in the length scale of our mesh. So we're going to try to look at that and we're going to try to discern what these are, how they affect our predictions. So CFD simulations themselves, they're composed really of primary flow structures. These are flow structures that have a dominant direction, and then secondary flow structures. And these secondary flow structures that we want to try to capture are kind of composed of both the structures that we can predict that are at the length scale of our mesh, as well as we use this turbulent viscosity to kind of capture things that are below the mesh. And this kind of brings up a good point. Basically, finer density meshes capture secondary flow structures that fundamentally change the required turbulent viscosity predictions. And this often hampers the ability to obtain grid-independent solutions of turbulent flows in geometries that are quite complex. Because, if the geometry is complex, the more fidelity you might add to your mesh, the mesh density gets finer and finer. All of a sudden, these flow structures are not approximated by the turbulent viscosity. They're actually captured by the mesh topology and your solution. So anyway, that's what the turbulence model is really going to do, and that's what we're going to kind of look at. And another thing that we're really interested in looking at in this discussion is not really what turbulence model is better than one or that. We're really we're going to look at this U-bend and we're going to kind of exercise turbulence models and try to discern, what can we really get out of these tools for a particular problem. But to kind of just start this, maybe we should start by looking at a simpler problem than U-bend to try to get, kind of an understanding of what these flow structures are and how they behave. So the example I have chosen here is basically a very simple flow through a duct, where we're going to kind of assume a uniform flow over here on the left-hand side. It's going to travel from left to right, and we've put a little flat plate here and a little pipe, and we're going to say this is half of the duct. So this line right here is the center line of our duct, and then the flow goes out here. And we're just going to use standard air to look at what kind of predictions we get here, but we're going to look at two different length scales. So the pipe is on the order of 2 inches. So we're going to use a very large coarse length scale on the order of 2 inches. And then we're going to look at a much finer length scale on the order of 1/4 of an inch. And we're going to use kind of a nominal velocity field of 3.5 meters per second. And all of the things that we're going to really look at in this discussion are going to be focused on steady state simulations. So let's take a look here. And so here is kind of a matrix of the nominal velocity field you would get when you run these simulations. So the top row right here is at the coarse length scale. And on the left-hand side is the prediction for the K epsilon turbulence model. And on the right-hand side is the prediction for the K omega SST turbulence model. And then the second row on the bottom is the prediction with the K epsilon turbulence model at the finer mesh length scale at 1/4 of an inch. And on the right-hand side is the prediction with the K omega SST turbulence model. And you can see that there are differences between all of these predictions. But in general, the bulk flow field follows a very similar trend. Basically, the solid surface diverts the flow, it accelerates and goes around. So there's some downward motion here. And then there's some acceleration because you're kind of pinching off the flow, so the flow has to get higher based on, conservation of mass. And then you have a secondary eddy that forms on the back side of this plate. So that's kind of the general flow structure that we're going to look at. But the question really is what does the turbulent viscosity look like for this? And here you can see this is the turbulent viscosity for all of these same fields, kind of in the same format. And you can see especially the difference between the K epsilon turbulence model and the K omega SST turbulence model. There's a marked difference in the turbulent viscosity, especially right around the plates where the turbulence is being changed. There's a large transition in this area and in this area. But over here, there's basically a higher turbulent viscosity in this area. And let's keep in mind that the turbulent viscosity, it really is kind of the measure of the diffusion, how much mixing potential our flow really has there. So anyway, we have the 1/4 inch length scale and the 2 inch length scale right here. So this is what the turbulent viscosity looks like. So let's just go and look a little bit more closely at the fine mesh length scale for this. And so here we have the fine mesh, and this is the prediction of the velocity field on the left for the K epsilon turbulence model, and this is the prediction on the right for the K omega SST turbulence model. And down on the bottom, these are our viscosity predictions between these two turbulence models. And keep in mind, we're not trying to decide which one is better than the other. Really, the purpose of this discussion is let's just kind of look at the differences between these two. And this is what we would see if we exercise these turbulence models. So anyway, so the turbulence model for the K epsilon says that the turbulent viscosity is high, so there's a lot of mixing right here, whereas the K omega SST turbulence model in this particular case indicates that the mixing potential is going to be reduced as it goes around the corner. So you'll also notice right here, I kind of have this line here that is right at the center line of where this eddy is, and you can kind of see because of how the flow structure goes around here. There's not as much diffusion, so in the K omega SST turbulence model, the flow is allowed to get much closer to the surface, so then it has a downward velocity a little bit more, so it allows the flow structure to kind of go down, and it makes that recirculation bubble be a little bit larger. You'll also notice here in the K epsilon turbulence model that the turbulent viscosity is much higher in this area, in that transition area. And here that means that the mixing potential is much higher in the K epsilon turbulence model than the K omega SST turbulence model. And therefore in the K epsilon turbulence model, you'll notice that the velocity structure and the mixing happens more quickly, whereas you kind of have a fine line in that velocity gradient that persists much longer. So that's kind of the observations that we have here between the differences between the turbulence model, the velocity structures, and how the velocity structures really respond to the differences in the predictions of the turbulent viscosity. So now let's look at the secondary flow structures. Here we have, on the left-hand side, we're looking very closely right around this plate and the pipe, and you can see that the pipe is resolved more closely in the fine mesh structure, whereas in the coarse mesh structure it is segmented, which is just kind of a product of the mesh length scale that we chose. What I've shown here also is it's not smooth contours. These are the values in each one of the cells. So you can kind of see the cell structure there. And one thing to really note here is in the coarse mesh, there is really no secondary flow structures in this area, whereas in the fine mesh, we've actually captured the secondary flow structures. And likewise, we can see here that the turbulent viscosity in the coarse mesh is much higher than the turbulent viscosity in the area where there is the fine mesh, because now the diffusion in this area is really kind of captured by the velocity field itself, because we've captured some of that secondary flow structure, whereas over here we did not capture it. So we're relying on the turbulent viscosity to control and have that additional mixing that kind of approximates that flow structure. So this is kind of a good example of how the mesh itself plays a role hand in hand with the turbulent viscosity itself to try to capture the effects of turbulence in this area for the mesh length scale that you might select for the problem that you're solving. So here, kind of just a final discussion after this simple example is that the turbulent viscosity is really, it is a mesh-dependent variable because you choose the division between what flow structures are captured and what are not. And so then the turbulent viscosity needs to respond to that. Secondary flow structures are characterized both by the predicted nominal secondary velocity field along with the turbulent viscosity field. The balance between resolved velocity structures and approximated velocity structures through turbulent viscosity can result often in conflicting predictions if there's a high gradient scalar field that happens to pass through that area. And that it gets challenging when you're trying to do mesh independent studies, which I discussed before, is sometimes trivial changes in mesh topology. When you change the density of the mesh, it really can result in a significant variation in predictions that are dependent on these secondary flow structures. Think, for instance, if a high stratified temperature flow field or a mass fraction flow field passes through these secondary flow structures, you might get noticeably different predictions in some cases. So now let's move to our U-Bend duct here and kind of let's get familiar with what we have and what this test case really is. And what it really involves is a square section duct right here. And you have a very long entrance length to basically an elbow where you go around the corner. And what we have are experimental data at fixed positions right here. We have one right at this beginning of the bend because the flow is kind of going in this direction right around here. And then we have another one here, 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 and here. So basically at, what would it be, 5 different positions around there. And we have 3 traces of of a probe through the duct right here. One right on the center line at each one of these locations, and one halfway between the wall and the center line. So that's kind of the data that we have. The fluid in this particular system is standard air at a standard density and viscosity. The velocity on the inlet is on the order of 11 meters per second. And if you want to know more about this, you can find it right here at this reference. So, like I said, we're going to really kind of exercise and kind of suss out what is going to happen if we change things and what kind of differences we have. And then maybe if we kind of know how things change, maybe that will give us a little bit of a perspective on what values we can kind of rely on as quantitative values and what values are more qualitative. And that's one of the things that would be nice to really understand. And this is a good test case to do that because we have experimental data. Most of the time when you're doing the commercial application of CFD tools, you don't have an answer. And sometimes you have to make judgment calls on what things are qualitative and what things are quantitative. And hopefully by looking at some of these where we actually have the answer will give us some perspective when we have to judge what kind of predictions we have when we don't have the answer. And so to do that, we're going to kind of look at a matrix of various different things. We're going to look at two different software tools. We're going to look at Azore, and we're going to look at ANSYS Fluent. And we're going to look at two different turbulence models, the K epsilon turbulence model and the K omega SST turbulence model. And we're going to look at the differences that we might see in the predictions for this case. And then we're going to pick three different mesh topologies. We're going to pick one mesh topology that is kind of a high Reynolds number mesh topology where the length scale near the wall is kind of geared toward having a wall function approach. And then we're going to look at some low Reynolds number mesh topologies where the mesh length scale is pushed down to the y plus of 1, where you're kind of attempting to capture the boundary layer itself. So here are the mesh structures that we chose. So we're going to kind of stick with a uniform length scale in the middle of around 3 millimeters, but we're going to kind of change the length scale of the mesh around the perimeter. And here we have a very fine mesh. And so this is kind of two different approaches for capturing that boundary layer. This approach for a boundary layer is often referred to as an inflation layer, where the mesh structure on the perimeter is kind of pushed in, and then the mesh structure on the inner part is kind of developed from that. Whereas on this mesh structure, it's more of a rows and columns where the cells are kind of bunched up along here, and you get kind of Cartesian cells rather than these like irregular cells around the corner. So those are the three mesh topologies that we're going to really look at here. So let's first start by looking at the basic flow structure that we're kind of expecting in this U-bend. So here, right here, is the total velocity as it goes around the corner here, and you can see that the velocities are on the order of 15 meters per second around here. And so this is where all the kinetic energy is in our fluid, and that's the most of the energy that we really have. So if we also look right here at this cross section, we can look at the secondary flow structures that develop in this type of problem. And you can kind of see if we just look at the secondary flow structures, kind of the in-plane total velocity, the magnitude of those are quite small, on the order of 1 or 2. So significantly smaller than the primary flow structures. And those flow structures are more akin to the turbulence model, and they're sensitive to those predictions. And the solution right here is, just for discussion purposes, is based on the K epsilon turbulence model using mesh M3. So let's just kind of, generally speaking, let's get familiar with how the flow structure develops as it goes around the bend here, and we're going to look at the different cross-sectional velocity, nominal velocity fields here. And here is kind of the inside of the bend surface right here, and this is the outside of the bend surface. So this right here is the inside and the outside, and then we have the different angles. 0 angle, that's right at the beginning of the bend, 45, 90, 135, and 180. And so you'll notice right here at the very first, there are no secondary flow structures. Really, the flow field is kind of gravitating toward the inside of the duct as the fluid kind of senses that bend, and the fluid begins going downward toward the inside of the corner. At the 45-degree angle, now our flow structures have begun to develop. The inertia of the fluid has traveled to the outside of the duct, and because of continuity, it needs to go somewhere, so it begins forming these counter-rotating vortices. And you can kind of maybe interpret, we kind of are developing a tube that kind of goes around our elbow. Right here, this is one tube, and there's a secondary tube of these rotations. But the interesting thing about this problem is right at 90 degrees, you'll notice that we have these two tubes there, but we actually have kind of a deficit right here. And if we look right down here, we have another tube that is beginning to appear right on the inner wall. So we have yet another secondary flow structure. So these are the small flow structures that begin developing, and it kind of begins as a point and then kind of grows in size. And so like the mesh length scale that we choose is going to kind of dictate when we can actually resolve it and when we're going to have to rely on the turbulent viscosity to approximate that flow structure down here. Then you'll see down here at the angle 135, you'll also see that this secondary flow structure has grown quite a bit, so much so that it's begun to distort this other flow field right here, where it becomes smaller over here, so that it's almost beginning to break down this flow structures. So we have, this is more of our secondary flow structure that is changing as it goes around the bend. And then at the 180-degree mark, all of these secondary flow structures begin to die out because we don't have the inertia of the fluid being thrown to the outside of the bend now, so it's just kind of dying out, and we just have a weak portion of those secondary flow structures. And so really what's happening here, and what our turbulence is doing, and the secondary flow structures that we actually capture in the CFD model, is it's moving around this high energy primary flow structure from side to side and around this duct. That's the purpose of it, and we're doing that by actually capturing the flow structures here, or by using the turbulent viscosity to kind of spread out those primary flow structures. So that's kind of what we're really going to look at here. So now let's kind of look at the solutions themselves, at these where the data is taken, and we're going to start by looking at the primary flow structures. So that's the normal velocity as it goes around the bend. And those are those are the flow structures that contain the primary, like the kinetic energy, the most of the kinetic energy in this problem. So here we have, let's talk a little bit about how this data is going to be presented here. So what we have here is the x-axis is the normal velocity at each one of the planes. You can kind of see here. So this is, and these black ones are the experimental data. So you can see right here on the inside of the duct, the velocity is a little over 11 meters per second. And then as you go away from the wall of the duct, it increases in velocity. And so this is the distance from the inside of this duct to the outside of the duct. And over here, this is kind of a picture of that flow structure. And so right now we're looking at the data on the center line. So this kind of red line kind of dictates and shows where that data is. And so here now that we're kind of using different colors and different line types to kind of differentiate between all of the different simulations that we have run, that we're going to kind of use to kind of look at the different predictions we might get as we exercise the different software packages and the different turbulence models. And so basically the bluish colors are going to be used for the mesh M1, the reddish and magenta colors are going to be used for the mesh 2, and the greenish colors are going to be used for our mesh 3. And so, and also the solid lines are going to be for the Azore predictions, and the dashed lines are going to be for the fluent predictions. And then the magenta, or this line right up here, each one of these, so we'll just kind of review this. So the Azore kinetic energy is going to be for the solid Cheyenne line, which would be this line right here. And then if let's pick another one. Let's look at fluent right here. For the fluent kinetic energy, the K epsilon turbulence model is this green dashed line, which would be this prediction right here. So for instance, if we wanted to compare the predictions between fluent on mesh M3 and Azore on mesh M3, it would be a comparison between this solid green line and this dashed green line. So it would be between this line and this line. And likewise for the red line right here, this would be for our mesh M2 between here and here. So that's kind of a rundown of these predictions and the experimental data and how that's going to be presented as we flip through these different test sections and look at this experimental data. So let's move to the next line right here. So here we're looking at angle 45, and we're looking at this angle right here, and you can kind of see the predictions here. And so maybe you can pause the video here if you want to look at it, but we're going to move forward as we look at each one of these. So here's the next one, and this one right here is kind of interesting because at this point we're down here looking at the flow structures right here, and you could kind of see there begins to be kind of a spread depending on the software package that's being used, but more so depending on the mesh topology that is used here. You get kind of a variation in the prediction of what the velocity is right in this area. And we're looking kind of at this line, and this is where we're really trying to capture right in here this secondary flow structure. And you see the experimental data seems to indicate that there is something going on there, as well as the CFD predictions also indicate that, but there is some variation in the predictions. And this is probably a good example to kind of discuss where things are qualitative and where they are quantitative. If you look at the predictions up in this area, they're fairly regular. There is some, in terms of the magnitude, there's some differences in what it is, but primarily speaking, they follow very good trends, meaning that basically the velocity is high up here and it kind of has a bending shape. Whereas down in this area, this is more of a qualitative evaluation because there seems to be a pretty big difference in opinion around this area. So probably the predictions for our CFD tools are going to be a little bit less reliable in this area for this mesh structure that we're looking at, because we have this experimental data to look at. And this again is now at angle 135. And you can see again up in this area, our predictions are similar and follow the test data, whereas there's a fair bit of variation down here. Some of the mesh topologies and the predictions seem to capture this distortion in the velocity field, whereas some of them do not right here. And now we're all the way down at 180 degrees, and you can kind of see here the secondary flow structures have begun to dissipate as we saw, and so the dependence and on those secondary flow structures is now gone away, and so now we are able to capture and correlate a little bit better with the experimental data. So in this area, we're more along the lines of the quantitative predictions, whereas in some of the areas in the previous ones, we had areas where maybe it's more qualitative. So now we're going to look again at this same test data, but we're going to be looking at this line right here of the test data. And we're going to look at it again. It kind of follows the same theme. We're still looking at the primary velocity field and the normal to each one of these planes, and it kind of follows the same trend. Here we are at angle 45. and then angle 90. We're right here, and so this gets very tricky. Like in my opinion, like where this test data is taken could really have a big impact, because like we're really trying to predict the size of this eddy and the structure of it. And right now, this line happens to be maybe in where the velocity is clearly going up, but as you get closer and closer to this center line, it probably becomes more and more difficult to get a good prediction. Even, you know, this might even just in general be moving around. The unsteadiness of that secondary flow structure could be moving around. And so now we're at a 135, and you can really kind of see in the test data, not so much, but it's certainly in the CFD predictions, you see just a little bit of a distortion here, and that's where the secondary eddies are beginning to impact that large primary eddy right in here. And now we're at 180 degrees, same thing. We're still kind of in this upward velocity. But as we saw before, the predictions become more reliable and closer to the trends. Now that's not right on to the data, but it's closer to the trends, and the fact that you kind of are all velocity fields, not much variation, but it's higher here and lower here, and that's kind of what our CFD prediction is giving us. And this is kind of a line between, yeah, it is kind of quantitative in the fact that the trend along here, but more qualitative in its magnitude. So the next thing we're going to look at are the secondary flow structures, and we're going to kind of expect that these are going to be, there's probably going to be more variation because it's more dependent on the secondary flow structures and at our turbulence model and how it interacts with the capturing of those secondary flow structures via the turbulent viscosity or actually capturing the velocity field. So here we're going to first start, and so now this is the radial coordinate, but we're looking at the radial velocity here. And you'll notice that the experimental velocity kind of indicates that the velocity is going away, whereas our CFD predictions pretty uniformly say it's going downward right here. So maybe the experimental data is indicating that some of those secondary flow structures are maybe in this area as well, forming. And so let's move on. So now we're at angle 45, and you can kind of see the same trends here. There's a little bit of spread, but it kind of captures the general trend of what's going on there. Here we are at angle 90, and now we're beginning to see quite a bit of differences in opinions about what's going on here, especially since there seems to be a lot of reverse flow in that area, which means that this eddy is going like downward here as opposed to upward with these negative values, whereas the experimental data kind of indicate that it's all going up. So here now we're at 135, and now you can really kind of see the spread. There is a lot of variation in the predictions for each mesh structure and even each turbulence model, as well as the differences between these models. So, and that is probably not surprising in this particular area, because now we're really relying on the turbulence model not only to capture these secondary flow structures, but also capture the struggle between the distortion of this velocity structure over here and the growing of this secondary flow structure. So it's not surprising that we're going to see a fair bit of variation at this particular location. And so this one, it even begs a question about, you can't really even look at it qualitatively in this area, other than the fact that you can say it's mostly going negative, which doesn't really kind of match the data that seems to indicate that it's going in the positive direction, which would be up right here. So this is kind of a good example of how you can really see a lot of differences from your turbulence model. So now we're at 180, and things, I mean, the predictions over here are maybe a little bit closer than the previous one, yet quite a ways away from the experimental data. Experimental data for secondary flow structures in general is probably a little bit more challenging to capture. So, you know, people who do CFD simulations often say, well, how good is this data? And that's probably another question that could be brought up about this data. But this is the data that we have, and this is the data that we're trying to correlate with, and this is the data that we're using to try to get a kind of a perspective on the reliability of our CFD predictions. And so now we're kind of going to go through the same set of slides, only we're going to be along this line, and maybe I'll just kind of quickly flip through these here. As you're watching the video, if you want to look at one more closely, you can pause the video and take a look. But here again, we see kind of we're at that 135, and we still see quite a bit of variation in this area. Now we're at 180. So that kind of concludes all of the information I have on in terms of looking at the different parametrics that we chose here. And I think some of the takeaways I'd like to make sure we gather here is, in general, the primary flow structures, the ones that have all of our kinetic energy, those are probably the ones that are quantitative in nature in general. The secondary flow structures, they're a little less reliable in terms of the predictions that we see here. They're more qualitative, and that is really because we're depending, it's dependent on the turbulence, and there's really no good turbulence model or method for capturing exactly turbulence. That is, some people refer to it as the Achilles heel of CFD predictions, is what do you do with turbulence? And so this is, you can kind of see that in these secondary flow structures. So some of the other things that we might want to kind of just discern here is the differences we saw really between the two software packages for a particular mesh topology and a particular turbulence model. If you look at that in general, there's not a lot of difference in the predictions between Azore and Fluent, which stands to reason, because if you're using the same, if you're solving the same differential equations and you're using the same mesh topology, you would hope that the predictions between these two would be the same, because you're doing all of the same things mathematically. Of course, there are a lot of details and small things that change how these predictions really might be realized in the details of how things are implemented. And so that kind of brings up this right here, and this really brings up a lot of the why do we see such a large discrepancy? Even the mesh topologies, seemingly like very small differences in mesh topology, result in, well, like markedly different predictions. And why is that? And it really comes down to, like, for instance, false diffusion is always present in our CFD predictions, and it can have a pronounced impact on the ability to capture these secondary flow structures and the diffusive nature of turbulence. How are gradients calculated? Those also have a big, they play a big role in, gradients are important because they determine how things diffuse. And so how those are calculated, and the mesh topology kind of provides the framework for how those calculations are done. A lower quality mesh, in the corners where we had like very sharp angles, maybe it might degrade how those gradients are calculated. And also changes in just mesh topology in general. Those also play a role. So in general, what we really want to do when doing design work using CFD, we want to if we're doing design work, we want to prefer design choices that rely on our primary flow structures. Those are the ones that give us our quantitative values, and those are the ones, as you could see, at least in this particular test case, those are the more reliable. So we want to kind of gravitate toward using our primary flow structures if we can when doing design work. When we're designing and exploring different design simulations, we want to try to maintain some consistency between our mesh topologies, our mesh densities, and certainly we don't want to change turbulence models in the middle of our design work if we're doing comparisons between one design and another. So that kind of concludes everything that I wanted to cover here. Thanks for attending. If you are interested in finding out more information about Azore, or you're interested in more tutorials or content like this, please visit these websites down here and you can find more information.